have the rest of the semester, I believe, for the course on this slide. So this is pretty much everything we're doing between now and the end of the end. So today the plan is we're going to start by finishing off talking Chapter 12 homework. And then we will launch into Chapter 13 slides. And I did post those, and everybody's been printing them madly this morning, so that's good. So we'll be ready to talk about those. That's very much a continuation. I mean, there's a way in which they could make Chapter 12 and 13 just like one giant chapter, and I think they tried to split it just to keep things sane and humane. But they are basically a continuance of each other. For lab today, we are meeting. This is our last lab that we are going to be meeting for. We're going to be doing a lab on human mate preferences, and that's the Match.com lab. So please do bring your laptops. You do not have to have a Match.com account established before you come in, although we will have to create one. But you can, you can make it funky. And we're not actually going to be, I always recommend having a fake email address or some kind of junk email address that you can use for all the things that you have to sign up for that you don't really ever want to get contacted for. So I have a Yahoo account, for example, that I use for that. So we will have to make an account just so we can get access to profiles, but nobody will be looking at your profile and you will not be interacting with anyone. We will just be doing searches, and you can actually input on there, I am a man searching for a woman, or I am a woman searching for a man, and you can do both, so we can all do these searches without ever having to worry about what's actually on our profile. There are many nice things about Match.com for this kind of thing that we'll talk about. I have no experience with actually using the thing, but that's all right. We're gonna it works well for research. The term papers are due tonight. I've talked to a bunch of people about them lately, so hopefully everybody's in good shape with those. If you have issues with them, please talk to me as soon as possible, and I'm happy to help in any way that I can. Let's see. Next Tuesday, that's our last week. I do want to do one last quiz. So we never did it, so we need to do a quiz on Chapter 11, and also we'll do it on Chapter 12. We're not going to do one on 13, and we're only going to touch on 14 anyway. The plan is after that we'll finish off 13. I should have mentioned there's a homework due that's also, I knew I forgot something. Do have one last homework assignment for you too. That's for Chapter 13. And that's also due on Tuesday. And then Thursday, we're going to be talking human behavior. So I have sort of one last little lecture that I'd like to do on that, because there's lots of great stuff in that chapter. It's just so much fun. At least I think it's so much fun. And then there will be a lab report for the human mate preference lab, but we will not be holding lab during that time. We're just not going to meet. I will be distributing the final exams at that time. The final exams, so you're getting them Thursday, and then our final exam slot, I think, for this class is Thursday morning at 8. So at the end of that period would be Thursday at 10 on the 13th, and that's when the exam will be due. So whether or not you are actually physically present on campus or not doesn't really matter, because we're submitting electronically. Whew, I think that is everything. Any questions? You guys doing all right? More or less. Nobody wants to answer that. Okay, that's okay. So what I would like to do then is let's talk about these last few, or not the last few questions. Most of the homework still remains. So where we were, I think we finished talking question 1 with the lemming with the little inner tube, in that this demonstrates that anytime you have a cheater present within a population, that's going to sort of, that's, if you have a selfless population of cooperative individuals and you have one cheater individual that's not giving of itself, that individual is probably going to survive and reproduce, which is means that anything where you're doing something for the good of the group usually won't work out. That some individual that's doing it for something for the good of themselves will usually win out and have better reproductive success than you, even if it's good for the group. Number 2 is asking us to try to understand these relatedness coefficients, though, because ultimately how we understand a lot of the apparently altruistic acts that we see in nature are through the fact that we're that we're doing things, or individuals are doing things for relatives, and in that way they're benefiting. So I thought we could just sort of run through the relatedness coefficients we calculated, and then if we have any disparities, we'll put them up here, and then if we need to, we'll calculate them out manually and figure out where we are. So, excuse me. something in my throat all of a sudden. So Angela, I gave you B, C, and D, or no, I gave you A, B, and C. I don't know why I said that. So what'd you get for between grandparent and grandchild? 0.25. Aunt and niece. And cousins. 125. And then Jackie, you got the next two. What'd you get cousins, you and your cousin's kid? Sure. Which would be, I'm going to do this just to make it easier for everybody too, if they did it the other way. For you and your half-sister. Then I may get anything different or not know how to calculate one of these. I'm happy to go into them, but if we all understand it, then we'll just move on. Okay. What did you get? Kind of close, right? It's not the same number. So, I mean, the way I like to think of these, I think the easy-headed way to do it, which is good for me, is that kind of with each step, you're halving your relationship with the person. So, if we're starting, so you've got mother and father, and then I'm going to put my family up here, even though my sister doesn't actually have a kid. So this would be father, this would be a mother, this would be a child, this would be another child, so these would be siblings to each other. And there's a 0.5 relationship between siblings, because you get half of your genes from your mom and half of your genes from your dad, and there's a 50-50 shot that you'll get the same ones from each kid. So anyway, so there's a 0.5 relationship here. If this individual then has a kid, so what are we trying to do? We're trying to get to cousins, so I need to do more here. So let's just do this. All right, the male and female bit doesn't really matter in these cases. So there's a 0.5 relationship between parent and offspring. And then we're trying to go to our cousin's kid, so this person has to mate. So we're making another one. Let's make this one male just for variation. So that's another 0.5. So basically, if you're here, so that's your parents. If this is you, this would be your aunt and your uncle. This would be your cousin, and then this would be your cousin's kid. So we've got all these different steps. But basically, for each step, we have to do a 0.5 relationship. So we've got 0.5, and we just multiply these, times 0.5 to get over to your aunt, times 0.5 to get to your cousin, times 0.5 to get to your cousin's kid. So let's do that again. So it's 0.5 times 0.5. That would give you 0.25 to get to your aunt, times another 0.5 to get to your cousin, times another 0.5 to get to your cousin's kid. So it's just 0.5 times 0.5. Is that right? Did I miss any? Yeah. So it's 0.5 to the fourth power. So that would be, I think it is 0.0625, which is 6.25%. I think that's right. Is that okay? Like, do you maybe hit a wrong button or something? Yeah. The other way you can do it, honestly, is you can just start with 1 and then just divide by 2 to get to your parent. Divide by 2 again to get over here. Divide by 2 to get here. So like each 0.5, you're just dividing by 2. And that'll get you there. Oops. So it does work out. It's kind of a predictable sequence. There's the possible values are 0.5. If you divide that by 2, it's 0.25, 0.125, 0.06. Maybe it's not 25. Is it 5 or just 6.5, isn't it? What is it? Write down. It is 2.5. Yeah, that's right. Because 5. God, this is what happens if you're standing in front of people. You can't do math. At least I can't. And we can keep going. You know, 0.03125 and so on and so on and so on. But we can. This is a nice predictable pattern, and you should be able to figure it out for basically any reasonable relationship. So, if you go find your great-grandfather's cousin or something, you should be able to figure out your relatedness to that individual if you really want to. It's kind of a fun thing to do if you're sitting around at Christmas time and you want to try to figure out exactly how many genes you share with each of those people. That is a knowable thing. It's kind of fun. We okay? Any questions on this one? When you get in-laws, sometimes it's gratifying, or you can kind of just take heart that when you don't share genes with them, and like you can okay, that's all right. And don't actually share any genes with these people. All right, let's do this. So the next one are the bees, the haplodiploid things, which is everybody's favorite. I know some of you guys aren't particularly interested in insects, but I think they are one of the when we're talking social behavior, they're one of sort of the pinnacle achievements of selection in terms of what we've seen happen with them on these eusocial insects. So I think it's good to try to understand this particular explanation because it is a little bit confusing. So let's run through these. So Gracie, I gave you the first two. So what'd you get for these? Okay. It's kind of weird. Yeah, I understand why one would do that. It kind of depends on your perspective, right? So if you're like comparing how many of the genes does the male's genes does the mother have, it would be kind of 100%. Like she had, all of his genes existed in her. But then if you kind of look at it the other way, how many of the mother's genes are shared by the male offspring, it's kind of 50. I don't know. When you look at this in the literature, a lot of times they do indicate 50%, but I understand why it's not straightforward because kind of depends on which way you're comparing it. And that's okay. Like I think it's good to sort of wrestle with that for a second and just recognize that it's a little bit ambiguous. But this is what you'll see in the literature. But it does depend on kind of like how you're doing the comparison. What about father and female child? There's a little bit of the same issue here. So this one went to Kayla. You got the next two. Yeah. You got one? Okay. What about then, I'm going to throw this one up too, and then we'll talk them all out. Ashley, what'd you get for E? 0.25. Anybody have any differences? I already kind of said this one's a little ambiguous, but anybody else have differences? Yeah? Seeing some nods. I think it is 0.75. The reason, and again, I asked you to do this before we had a chance to do it in lecture. But the reason is, so it's not 100%, because when you're looking at a female offspring compared to a sister, there is some segregation that does occur there because the female does make multiple different kinds of gametes. So a female's eggs there's basically, there'll be a variety of female eggs as she's independently assorting each of her chromosomes into those gametes. She's going to give one of each kind of chromosome to each gamete, and that will result in a variety of gametes being formed. So in this case, if we're assuming she just has 2 chromosomes, just to make things a little bit easier rather than actually going to the number she actually has. So if we just go with 2, there'd be 4 possible combinations of those chromosomes that she would create in terms of the types of gametes she'd make. Each of those, though, would mate with one kind of gamete that any one male could make. Right? Males can only make one kind of gamete because they're a haploid genotype anyway. I mean, that's all they have to give is one of each kind of chromosome. So they can only make one kind of sperm. But then if you put them all together, you do still get a variety of daughters because they're getting a variety of chromosomes from their mother. So these are all not the same genotypes. We're getting a variety of daughter genotypes. So then if you pick any one of them, so if we pick this particular one, the blue, red, blue, blue variety here, and then you make a comparison of this one to each of the other possible combinations, you can compare up and add how many of the chromosomes are shared. This one has 3 out of 4 shared. This one has 3 out of 4 shared. This comparison would have 100%. This comparison would have 50%. If you average them all together, it does work out to be 0.75 shared. So a 75% shared relatedness between each of the sisters on average. The reason it's 0.75 instead of 0.5 is that they're all getting exactly the same genetic information from their father. What's different is which chromosomes they happen to get from their mother. They may or may not share the exact same chromosomes between their mother. So it should be 0.75 there. Strike that one. Are we okay with E? Because I think, if anything, E is harder. It's sort of the next step up. But the idea here is you have the same mother, but you have different fathers. We can actually flip back to that same figure to explain that one. So in this case, we're assuming they all have the same father, so they all got the exact same genetic info from their father, because the father can only make one kind of gamete. If they had different fathers, though, that means that they will not share these sort of 2 dotted chromosomes at all. We just wipe those out. So they're not shared. So all that they potentially could share is the information they get from their mother. So in this case, they would not share any chromosomes. Here they would share 2 out of their 4 chromosomes. The other 2 were from a different father, though, so they wouldn't share them. Here, they'd share 1 out of their 4 chromosomes, because again, they've got a different father. And here, they would share 1 out of their 4 chromosomes. So if you go through and add those up, that'd be 25 plus 25 plus 50 plus 0. Divide by 4. It does give you a 0.25 relatedness. I think that's the hardest. How are you feeling on those? Is that okay? Get some nods. All right. Good. Yeah.
For the E on number 3, I put 0.375.
Yeah. Well, like I said, I was just trying to run through how to calculate. I think it is 0.25. And again, the reason is that I think the way to do it, the way to actually figure it out, is if you sit there and you stare at this thing. If you understand this figure, this is comparing full sibs. But if it's half sibs where the father is different, you'd have to compare this individual versus all of her possible sisters. Sorry. Come on. All of her possible sisters when they have a different father. So there's a different genotype there. And that would give you this ability to compare half-sisters in this weird sort of system. Haplodiploid, I mean, I think the thing that's really interesting about haplodiploidy is that it is this mechanism by which you can have really, really different relatedness coefficients than we get through the normal system. We're used to having 2 diploid parents. But now we've got this system here that because of the sort of quirks of how haplodiploidy works, because they're getting all the same genetic information from their father, full siblings, sisters, end up with very high relatedness. On average, it's 0.75. And that's way more than we ever see. And so as a result, it becomes really beneficial to be supporting the production of new sisters. That's the great thing about it. That last bit is interesting, though, because we do have this big drop, right? We go from 0.75 to 0.25 if we're dealing with half-sisters. And so this final question says, based on what you calculated in D and E above, how would the average relatedness between female workers compare in colonies in which queen mated? I said one time, I was revising it this morning, so sorry about this. But where the idea is if the queen mated with 1 male versus with multiple males, how would this affect the relatedness coefficients? So what did you get, Ashley? Mm-hmm. What do you think implications for the social behavior?
So
Ideas?
my idea was that there wouldn't really be a difference.
Okay.
Regardless of like whatever the situation would be, the queen's always going to deposit at least like 50% of her genes. And so like in my opinion, I just thought that like no matter what, like worker bees are always going to be worker bees, and then like queens are always going to be like spread bee queens. So I didn't think that there would be a difference.
Okay. So they're already kind of locked into this system. So is that kind of the argument? So like she's already like worker bees are workers because they get fed different things than what the queens are fed. It's kind of hard to undo that. Like once they're sort of already committed into this eusocial system. And I think this is a fine argument. You'll see this argument in the literature as far as why this would be, because it is the case that like the workers are benefiting less, I guess, by producing a half sibling than they would by producing a full sibling. But they're already so into this system of eusociality and having these castes and sterile workers and these kinds of things. And the same would be true for a lot of these ant groups. They have just really, really strict castes with massive size differences and functional, some are soldiers versus workers, and they have very different kinds of morphology as a result. It's difficult to kind of undo all that. Anybody have another thought on it? This is a point of contention in literature. So like there are multiple answers to this question, I think. Agree, disagree? I'll give you the alternative take too. I was going to make sure we hit both of these. But the alternative take is that when relatedness is lower, workers really would start, especially if the relatedness between siblings starts to drop down below 0.5, which it does as soon as you start dealing with half sisters, then you might start to expect to see workers starting, like you might occasionally get mutations, variants where workers would start laying eggs and start trying to reproduce on their own, because they would benefit more from reproducing on their own now than they would from producing sisters, if they're able to successfully rear offspring on their own. So again, when relatedness is lower in a colony, so when relatedness is lower in a colony, you may expect to see some workers start laying their own eggs and trying to reproduce. I'm putting trying in quotes because I don't know that ants can really decide to try to do anything, or bees for that matter, because they're not benefiting as much from helping the queen raise more sisters. So selection should favor worker reproduction at that point. At least eventually it might. But again, like I think that argument holds better sway when you're dealing with a situation where there's a colony that's not really eusocial yet. There's just sort of like cooperative breeding going on, and there's a lot of helpers going on. But you don't have like these strict sterile castes yet. And in that kind of situation, there are examples of that in ants, which we get to later in this homework, I think. In those kind of scenarios, I think this could be a real problem as far as developing and evolving eusociality. Once you're already eusocial, there's an argument you kind of go over a cliff. And at that point, it's just like it's really hard because you have these strict developmental pathways and such. It can be really hard to sort of revert from that eusocial behavior. So there's an argument that it's difficult to find examples for where we think the ancestral group of a species was eusocial and they have lost that trait. In fact, I'm not aware of a case where we found an example of that kind of a thing. It seems to be something where once you kind of commit into becoming eusocial and you really start to have sterile workers and caste differences and that kind of thing, it can be very difficult to sort of undo that. So again, there's sort of two takes to that question. Makes it interesting. Does that make sense though? Questions? Ready to move on? All right, let's talk about something else. So naked mole rats are these adorable little, they're either adorable or they're just gross, and I can't really decide what I think about them. You may have your own opinions. But it says, in addition to monogamy and haplodiploidy, which are the two things we talked about in class, inbreeding has sometimes been identified as a factor that will make it more likely for groups to evolve highly social behavior. And so they talked about, the question talks about naked mole rats. DNA fingerprinting has found that they are crazy inbred in some cases because you have, and there was a result of that inbreeding. Well, it says, why would inbreeding make it more likely for eusocial-like behaviors to evolve, and what could be some costs that come from that? So this one went to Adam.
I said there would be little genetic diversity if every female would be able to reproduce and inbreed, so the colony would collapse. By only having one female reproduce allows this to slow down. And then, like, some cost would be higher rates of birth defects and being sterile.
Certainly we see, and this is sort of a well-known thing, as soon as you start inbreeding, you start exposing these recessive lethal alleles or damaging alleles that result in all kinds of weird birth defects or, you know, metabolic problems where you don't produce enzymes that you need anymore. And, you know, so those have got to be like major issues that inbred groups have to deal with and encounter. This is why you're not allowed to marry your own sister. Anybody have any other like additional thoughts on how this could impact social behavior within the colony? Sort of like one little thing I want to fish for. What would this do to the relatedness coefficient with inbreeding? What do you think? Yeah, so a thing, you could argue about if this is a good thing or not, but a thing that inbreeding will do, I'm going to put this up here. So if you have a mother and a father, and the mother and father are siblings, that means that the mother and father already share a lot of genes with each other, 50%, assuming they weren't from inbred parents themselves. So you have two related individuals that are interbreeding with each other and producing offspring, and that means there's a very good chance you could get an allele from your father that your mother also has, and your mother could give an allele that your father also has. And so the result is that your offspring have a higher relatedness coefficient than they usually would, because they're just kind of getting all the same batch of genes from both parents. And so the result is that they're going to share there'll be lots and lots of shared genes across the siblings. So comparing across the siblings, you'll have really high relatedness coefficients as a result of inbreeding. And it can get up to, 0.75-ish area. And that, so that you were kind of replicating what we were seeing in haplodiploidy through this inbreeding sort of process. That doesn't mean it doesn't come with massive costs. Sorry, I didn't realize I was off the screen edge there. Get on here. So the costs are still potentially very high. Inbreeding has lots of deleterious effects, and we've seen, that's, going back to your earliest genetics lessons, I'm sure you've been talking about that. But it does really increase the relatedness coefficient. And one of the things we've been saying is that the way in which you can get social behavior happening within a population is if there is a high relatedness coefficient, because then you've got a big payoff. You're getting, by helping your sibling or helping to produce more siblings, either way, you are sending more and more of your own alleles into the next generation through that relative. And so the higher the relatedness coefficient, the better payoff to social behavior you'll tend to have. Let me put that down. So inbreeding should result in better payoffs for social behavior in which you help produce more siblings, or you're helping your siblings to reproduce, because that means more of your genes that you share with those relatives are getting passed to the next generation. Okay? All right, last question. This one's, I think, just kind of fun. So not all ants are eusocial. In some species, female workers often do assist with carrying of offspring, but the workers remain capable of laying viable haploid eggs. They're haploid because they probably haven't mated. Based on discussions on pages 470 to 473, what kinds of sanctions do queens or fellow workers impose on rogue egg-laying workers? So Tyler, I'll give that one to you. What'd you get for that? Yeah.
I put workers may immobilize egg-laying workers for days or stop their ovaries from developing. Those were the ones that I found
Yeah.
directly related to ants.
Yeah. Yeah, there's a great picture in your book that shows, like, it's almost like they're being drawn and quartered, where, you've got multiple ants that are kind of like just pulling on this other ant's legs, and it's just, it's just in stasis, like, and it's basically that's ant jail. So you're in jail, so you've been immobilized, you're being punished as a result of egg laying. Are there any other things you guys saw? You said maybe there are a couple others that weren't ant related, but did anybody put anything else? The other one that's immediately just also coming to mind, and I think ants will do this, is also just like egg destruction, where you'll see patrols going around. If a queen finds someone else's egg, they will often destroy that other egg, so they can somehow tell, probably some kind of a scent cue or pheromonal cue, that would allow them to detect whether or not it's their egg, and then they just destroy those eggs whenever they encounter them. Because certainly from the queen's perspective, it's not going to benefit her. I mean, it benefits her some because it's probably her offspring, but she's certainly in the business of producing more siblings, and she wants her, from her perspective, it's not that she wants it, but selection will favor those queens that behave in a selfish manner and promote their own egg laying over that of their workers, because they have a higher relatedness to their own offspring versus some, like, grandchild, for example, that they would otherwise have. Any questions on any of these? Good? All right. So I would like to do a quiz on that chapter 12, as well as chapter 11, the parental behavior one. We'll do that on Tuesday. That'll be our last quiz of the semester. We'll move on from there. Boop. All right. Let me close this door. It's a little noisy out there. Okay. So with that as our backdrop, in a lot of ways, I feel like the whole point of that last chapter is trying to understand how it is that we can have altruistic behavior without imposing group selection as sort of like our explanation for it. And the argument throughout the thing is that when you help your relatives by being altruistic, if you're helping relatives, then those genes that you share with those relatives may be passed on to the next generation, and so you can benefit in that way. Your genes are being perpetuated even if you're not directly doing that reproduction. This is this inclusive fitness benefit idea or the kin selection benefit idea. And that does directly impact and help us understand why eusocial insects that are like completely altruistic and giving of all their reproductive success work. But it also can have implications for how we understand other kinds of social behavior. And that's what we're going to be trying to focus on for the most part within this chapter is social behavior in general. So we're kind of taking a step back and trying to understand how it is that animals interact with each other. So we'll talk a little bit at the start about costs and benefits of social behavior, and then we're going to run through a couple different varieties of social behavior, cooperation or mutual benefit behaviors, postponed cooperation, which is kind of the same thing, but it has a little bit different. Reciprocity, which is also kind of the same thing, but also a little bit different. And trying to use these principles to understand why you have certain interactions between animals. And then we're going to sort of put all these things together along with the last chapter in a case study on Belding's ground squirrels, which are a lot like prairie dogs, that we'll talk out and work through. So that's our plan. So the first question that, just to kind of kick this off, is why one might opt to live in a social group. And we talked a little bit about group behaviors and grouping behaviors before, as far as what are costs and benefits to living in a social group. I thought maybe we could kind of recap some of those. If you think back to some of those, I don't know, that was probably like chapters 4, 5, 6, something like this, when we're talking about where animals live, how they move around, living in groups, anti-predator behavior. So what are some of the costs and benefits to living in a social group that you remember or you can think of? I just want to make a quick list. What do you remember? Yeah. Sure. So dilution effect, selfish herd, these kinds of ideas, we talked about those things. What else comes to mind? Other things that might be benefits or costs? Yeah. Yeah. Others? Yeah. Certainly don't have to go far to find another of your own species, which can be a problem for dispersed ones. Yeah. I'll throw parasites in there too. Other things? I'll just throw these up here too because we talked about them. There are other mates around, but there's also competition for those other mates potentially. So that's a problem, especially if you're a male. Females usually can find a mate, but for males it can be more difficult if there's sort of a dominant male in your group and you're trying to find a mate and you're going up against the dominant male. Even if it's your father, you're probably, if they're still healthy and in good condition, it might take a while before you're competitive with that individual. Inbreeding, since we were just talking about that was another thing we hit. So a lot of times you see dispersal to avoid this kind of a problem, especially among males, trying to get away from native groups so you can find females that you're not related to mate with. It's a pretty good list, right? So this is sort of the idea of living in a social, or in a group in general. And a lot of these are, I think the thing about the benefits anyway that we're talking about, maybe not the available mate one, but the predation protection one, you just kind of have to be living around other individuals. You know, like you're not directly having to interact with them in order to achieve that benefit. And what we want to do, I think, in this chapter is better understand what are some of the benefits that one receives from explicitly socially interacting with other individuals. There definitely are costs. So, I mean, this is sort of building off what we just talked about. There are definite costs to living in social groups, and parasite load is one of the big ones. I always love, have I shown you this picture? I don't think I have. I had been in prior lectures, and I pushed it back to this one. So this is a cliff swallow. And these guys live in large colonies on cliffs. We've talked about them a little bit in terms of their recognition systems that the chicks have, that the parents use to detect them. But in this, the problem, one of the problems that cliff swallows encounter is that because they live in these large colonies, they get infested with these mites. They're called swallow bugs. They're kind of like a bed bug. And these things basically just creep up to the chicks that are sort of helpless sitting in their nest, and they bite them and they suck their blood. And usually I think we tend to think of mosquitoes and bed bugs as just kind of like really annoying and gross, but not like directly impairing your growth. But it actually can result in a really large cost to these individuals. So what you're seeing in this case, these are two chicks that are actually exactly the same age. And what the difference is that this is your control chick, so nothing really happened to it. This is a chick where they fumigated its nest site with basically anti-insects pesticides. And as a result, they killed all the swallow bugs. And so this is what happens if you allow these chicks to develop without having this parasite constantly depleting them of their resources. Because there's a lot of these damn bugs, and they're constantly sucking their blood. So this little individual has it takes him or her, longer to develop adequately to get to the point that this one was able to get to much more quickly because it's not losing its resources. So parasites really can have a dramatic effect, and disease can have a dramatic effect, certainly, in terms of development of these organisms. There's other kinds of cost to group living. So competition from food and mates, we just talked about, is an issue. Inbreeding is an issue. So because of all this, there has to be substantial benefits to living in groups. One of those benefits has definitely got to be anti-predator sorts of benefits. That's one of the ones we've talked about in prior chapters. But there probably are some other benefits, and a lot of those are related directly to living in social groups. So the direct interaction of individuals is sort of the key thing here that we're trying to focus on in this chapter. This is a figure from your textbook that I think tries to summarize kind of 4 major outcomes of social behavior. And it's in a way I like it a lot. In a way I think it's sort of needlessly complicated, especially all this stuff on the inside. It's kind of not necessary. What they're trying to do is they're saying, all right, so for any given social interaction where one individual does something to or with another individual, there'll be a donor. The donor is sort of like the doer of the action. And there'll be a recipient. And the recipient is the one that's sort of receiving that action. There's these can be all kinds of different interactions. And so what they're trying to do in this figure is they're dividing it up into 4 sections. And each of these 4 sections is different based on whether or not the donor is benefiting, which is this one, or is the donor being harmed or suffering a cost. And also, is the recipient benefiting, or is the recipient suffering a cost? So, for example, if the donor is benefiting from an action, and then the recipient also benefits from that action, that fits into this category up in the upper left. This is a mutual benefit. Or you could, a lot of times we would call this a cooperation. I actually don't like cooperation being down here. So this is a mutual benefit to those 2 individuals. And that's what they're trying to show with these 2 pluses in here. They're just sort of, that red plus has gone down here, this black plus is here, so they're both benefiting in that situation. If I was going to I might just make the figure again next time and just do it as a 4x4 grid and get all this crap out of here, because I think it gets confusing. If the donor benefits, but the recipient suffers a cost, this is what we would call selfishness. So this is, you're doing something for the betterment of yourself and it's directly harming some other individual. So you could, an example would be like stealing food. If you steal food from another individual in your group, you directly benefit from that and that other individual is harmed. Very straightforward. So that'd be a selfish behavior. Then there's those cases where the donor gets harmed. So if the donor pays a cost for a behavior, but then it benefits a recipient, that's where what we would call altruism. And if it's true altruism, this would be altruism where where the donor really is suffering a fitness cost, and they're not having, through some sort of kin selection argument, they're not benefiting from the thing. So true altruism would be a loss to the donor but a gain for the recipient. And then there's the final category, which you don't see super often, at least not obviously in animals, which would be spite. And this is where the donor harms themselves and pays a cost, basically with the goal of harming the other individual too. So both individuals suffer from that situation, which usually is not an advantageous situation, and therefore selection does not favor it. For some reason, some people seem to be insistent on doing this, but I don't understand why. All right. So what I want to do is basically walk through, especially these two, because I think these are the most interesting. Selfishness, I mean, this is something that happens all the time. Darwinian, this sort of, the idea with Darwin and the struggle for life does sort of indicate that this is something that is usually going to be a beneficial thing. I mean, there's a way in which any kind of animal basically makes a living out of this, because all animals live by eating other organisms, be it a plant or be it an animal. And so that, by its very nature, is kind of a selfish sort of an act. That's just the way animals are. But I want to focus on the two where the donor is benefiting, well, the two where the recipient is benefiting. So mutual benefit will be a case like a cooperative sort of an act where you see animals that are interacting with each other within a social group, and they're both benefiting from that particular interaction. So a classic example, if you're watching wildlife shows on TV, you see these awesome hunts that, lionesses or hyenas do this, or, other wolves do this, where a lioness, they will work together cooperatively. So you might see, for example, one lioness driving a wildebeest into an ambush that's set by other lionesses. So you basically drive the wildebeest in, and the other ones pounce on it, and then they all get to eat it. So all of them benefit by getting the prey. The other lionesses benefit from this one lioness's action because they get to eat, but then the female lioness who spooked the wildebeest to begin with also benefits. So this is a cooperative mutual benefit type of an action. Nice and straightforward, right? And we do see these kinds of actions oftentimes when we're dealing with, when you're looking at social groups. You see this kind of cooperation. Sometimes the mutual benefit is not as obvious, though. So here's an example. This is in wasps, but there's all kinds of examples of this. And some of these appear in the homework again, so we'll return to them. So in these Polistes wasps, these are paper wasps, you end up with a queen, effectively, who's doing basically all of the reproduction. And then you also have subordinates that will also work at this nest. And the subordinates basically don't get to breed. And they may be relatives of her, so you can make an inclusive fitness kind of an argument about what they're doing. But sometimes they're not even relatives of the queen, and they still will help at this nest over a period of time. And that's kind of a puzzle, right? I mean, it seems like that's an act of altruism where the subordinate individuals are giving up their own reproductive success for the benefit of the queen, the dominant female, who operates at that nest. The interesting thing is, though, that sometimes you can actually figure out that there are benefits to those subordinates. It's just the benefits might not be happening right away. So this is why it's sometimes called postponed cooperation. And this is what this figure is trying to show, is that if you look at the per capita, so this is per individual number of pupae that individual wasps were able to raise. If you look at, so subordinates sometimes do get to lay eggs within these nests, just not real often. The dominant females really are the main egg layers. That's the blue line here. And what you end up seeing is that as group size increases, maybe they get a few more opportunities to lay some pupae, but again, they're not getting very many offspring. This is basically how many offspring are you getting? And they're not getting very many offspring. However, these subordinates, if they stick around for long enough, what eventually often happens is that the dominant female will die or otherwise disappear, and they will inherit the nest. And if they inherit the nest, their reproductive success goes up dramatically. So those subordinates who ultimately then later inherit the nest, their lifetime reproductive success in terms of number of pupae raised really shoots up. And so it seems as though the benefit to the subordinate is that they are sticking around, they're staying at this nest, and they're hoping to later inherit the nest and benefit then. So they're not benefiting now, they're paying a cost now, but they will benefit later. So by helping, certainly the dominant female is benefiting immediately. So that's a benefit for her. But the argument here is that selection's favoring subordinates that do this because they will later benefit, and they will also get a benefit later on. So this would be a mutual benefit situation. It's just a delayed mutual benefit. It's a postponed cooperation. Part of the reason this works is that if those subordinates just try to go off and found their own nest, that's this bottom line. It's kind of hard to tell. These are red, these are orange, but this is this bottom line. These are solitary foundresses that try to just go it alone. And those individuals have a very difficult time having good reproductive success. It's hard to start a nest on your own, and it's often much better to inherit the nest later on. So you can make an argument the subordinates are kind of making the best of a bad situation. It's hard to go off and make your own nest, so maybe stick around. If you're lucky, before you die, the dominant female will die, and you'll get a shot at reproduction. Here's another example that kind of looks like it might be altruism. And this is grooming that you see in baboons. So what you're seeing in this picture, these are, I don't know how you pronounce this, Hamadryas? It's probably right, Hamadryas baboons. This is a male, this is a female. And at this moment, what you're seeing happening is that this female is preening him. So basically, she's going across his leg, and oftentimes you'll see these guys sitting with, the one individual's back is to them, and they're going through their hair and grabbing bugs and stuff out of them and pulling and preening, and as a result, this male is benefiting from the female's actions here, in that she is ridding him of ectoparasites, which can have a substantial cost. So at this moment, the female is basically paying a time cost. They'll spend hours doing this. So this is a substantial amount of time. So she's paying a cost, and he is directly benefiting. So it appears to be a situation where you kind of have an altruistic act that's going on here. The interesting thing about this, though, is that if you keep watching these baboons, and certainly there are researchers that spend tons of time just watching individual troops of baboons and recording all the behaviors, what you'll eventually see is that this individual, the male, will at some point effectively pay back the female. And there's a couple of different ways this will happen. You'll see individuals that have been preened before, have been groomed before, go back to that same individual that previously groomed them, and they will groom that individual. So they'll kind of take turns grooming each other. This is sometimes described as like a tit-for-tat relationship. I will groom you if you will later groom me. And so there's this kind of reciprocal exchange where right now I'm going to pay a cost, but later you're going to pay the same cost for me, and therefore I'll benefit from that. Another way, especially in the case where you have male-female sort of a difference, these males, you can tell that the male is substantially larger than the female, and males will protect those females that perform grooming for them. And so this is sort of another way that males can help to sort of pay back favors and on the part of the female. They'll protect them from other males within the troop. The males can be very aggressive, and so by having males that you're kind of forming an alliance with, the female can directly benefit from the action that she's taking at this moment. So this kind of a scenario where you have, it's not just that your benefit is delayed, but it eventually will be paid back. It'll be paid back by the same individual that you're currently that you're currently helping. This is often originally it was called reciprocal altruism, or a lot of times now we just call it reciprocity. This is, again, this tit for tat. I'll scratch yours if you'll scratch mine. And so in this way, really, it is another scenario where you have a mutual benefit by both individuals that are part of the relationship. The key thing is that you have to kind of play the long game with this and understand that this is a long drawn out kind of a situation where you can't just look at one particular act. You need to look at over weeks of time what are they going to be doing with one another, and oftentimes they're going to be paying each other back for services rendered at a prior time. This is another example of reciprocity. These are vampire bats. It's a little hard to see them up there. Vampire bats they're really interesting for a variety of reasons. They're these extreme specialists. We talked about them earlier in the semester. They don't seem to be able to associate negative experiences with food, which is kind of neat. They literally kind of live on the edge, though. They are super high metabolic creatures with relatively low body mass, relatively low energy stores, and they go off and they forage nightly, and when they're successful, they're usually going to be able to receive a large blood meal. Blood is not particularly nutritious, but they will get more than they're able to actually process and that they actually strictly need. And they basically store that all away in their gut, and then they head back to the roost with the plan is effectively that they're going to digest that over the course of the day. The problem is if they don't go off and get a successful blood meal, then they may literally be in danger of starvation because, again, they kind of live on that metabolic edge. They probably could make it a day, but they'll be in worse shape the next day. And on the next day, if they don't get a blood meal, they really are very likely to not survive at that point. So one thing you often see in these colonies of vampire bats is that if somebody comes back and they were unsuccessful foraging, then the successful foragers will often share a bit of their blood meal. They basically regurgitate some of the blood and allow the other individuals to drink it. They share the blood meal that they found with unsuccessful foragers, which again looks a lot like reciprocity, and looks a lot like altruism. They're not necessarily related to the individuals that they're sharing with. They will often share with the frequent roost mates, but they're not typically going to share with brothers or sisters or something. So you can't make a kin selection inclusive fitness argument of why they would do this. They are basically giving up some of their meal, some of this nutritional benefit that they've gotten for the benefit of other individuals. The argument for why they're doing this, though, is that they are, again, they're not ever only going to encounter these individuals one time. They're coming back to the same roost every night. And the same individuals are coming back to the same roost every night. So if they share with another individual now, there's a good chance that a few days from now, if they're unsuccessful foragers, that same individual will pay back that favor by sharing back with them. So they do seem to share, they will share with frequent roost mates. If you throw in some strangers and within the group, and people have done this experimentally, those new sort of foreign individuals will not get shared with. So they won't receive that kind of a benefit. So again, the story here is that this is reciprocity. You're benefiting, you're giving of your own, you're paying a cost now and benefiting another individual now, but you'll receive a benefit for that later on. You'll have that paid back to you. This is kind of like a paying it back kind of a system. So this is a form of mutual benefit / cooperation. Short-term loss for one party, but a long-term gain for both parties in the end. Now, I think those ideas make some sense. They have been modeled with game theory. And so there's this old idea of prisoner's dilemma. I think it does a really good job of helping to really understand reciprocity in a little bit better detail. Have you guys run into prisoner's dilemma like in a psychology class or anywhere else before you've seen it? A couple nods or people saying yeah. It's a classic idea. It goes back to if you see the movie Beautiful Mind about, what's his name, Nash, I forget his first name, was the guy that first developed this idea. There's some discussion of at least sort of a version of this. But here's the scenario. And so we'll run through the scenario and then we'll try to come back and apply this to this idea of cooperative behavior. So let's imagine that you're involved in a crime with a collaborator. So you have some partner in crime. There is weak evidence against you, but you are caught by the police anyway, and you're taken to a cell. And the police come to you. You're isolated from your partner. You don't know what your partner is going to do. But they say, all right, so here are your choices. If you squeal on your companion, and your companion, I put he, could be a she, and your companion keeps silent, then you get to go free. So that's a major benefit if you squeal and your partner at the same time does not squeal, he keeps silent, then you get a massive benefit. If you squeal on your companion while he does the same thing, if he also squeals on you, you're both going to get convicted, but we'll convict you on lesser charges. So we're trying to encourage you to squeal. However, you know, or you sort of realize, they don't have very good evidence against you. So if you keep quiet and your friend also keeps quiet, they may be able to convict you on a really low charge. And so maybe you'll get 1 year in jail as a result of that. That does rely on you staying quiet, and your friend also has to stay quiet and not succumb to the offer that the police are giving you. But you know also that if you keep quiet but your friend then squeals on you, if they defect, then you're going to get a massive conviction, hard time, you're going to serve 10 years in jail. So that's the worst possible outcome for you. So this figure tries to summarize all of those different arguments. So we've got sort of a 2x2 grid again. Here is the action of player A, so let's say that's you. Here's the action of player B, that's your partner, and you don't know what they're going to do. But again, if you cooperate, and cooperate here refers to cooperating with your companion, not with the police. That sometimes can be confusing. That's the way this literature is phrased, though. So if you stay silent, you can even put a line through this and just say silent. If you're silent and your partner's silent, you're probably going to get convicted, but it'll be some minor charge because they don't have really good evidence against you. It'd be like 1 year in prison. But if you stay silent and your partner defects to the police and squeals on you, then you're going to get a maximum punishment of 10 years in prison. So that's no good. If you squeal on your partner, so if you defect to the police, but your partner stays silent, they're going to get maximum conviction, but you get to go free. So this is your best possible outcome. But if you defect and your partner also defects, so you both squeal on one another, you get sort of a medium amount of punishment. So you get 5 years in prison. The police will play nice on you because you squealed, but still at the same time, they're going to convict you both. So the question is, what should you do? This is your scenario. So what is your best decision in terms of what you should do, given that you don't know what your partner is going to do? You have to deal with that uncertainty in this setup. And it's frustrating because, if you defect, that's your best possible reward, but there's also a pretty bad punishment there. So what do you do? What do you think? Actually, I'm going to phrase it this way. So what's the best solution if you only are ever going to face this dilemma one time in terms of your personal success? You don't have to worry about your partner ever again. Never going to encounter this again. What should you do? What do you think?
Let's say if you're only doing this once, the
Yeah.
best bet is to work with the police, because the only chance that you have of facing maximum punishment is if you don't work with the police.
Right. Okay. So the worst possible thing that can happen is if you don't work with the police and you get 10 years. Like that's the worst. So you're avoiding your worst possible outcome there. Other thoughts? I guess by that same token, your best possible outcome is if you do cooperate. So that's good. I mean, there's a bad one here too. That's 5 years, but that's your best. That's what that would be the ideal thing for you probably. Other thoughts? You agree? Should you defect? You want to vote on it? Like who would defect? 3 people, 4 people? Who would cooperate? No, but 1. Lots of people just don't know. Like I like to be a nice person. My bias is to cooperate, but I don't know. I mean, if you look at this, a way to think about this is that, okay, let's say that player B cooperates. You don't know this, but let's just say they cooperate. If you defect on them, if you squeal on them, you get freedom. If you cooperate, you get 1 year in prison. So it is better to defect, right? If your player B defects on you, and you also defect, you get 5 years. But if you stay silent, you get 10 years. So again, it's better to do this. So it's always better in this particular scenario. It's always better no matter which option player B does. It's always better to defect, right? Even if it feels wrong like that. That is the best scenario if you're only facing this dilemma once. Here's another thing though. So let's say that you are committed and your partner is committed to a life of crime. Like this is how you're going to live your life. So you know that this is probably not the last time that you and your partner are going to go to jail, because you expect to spend the next 60 years of your life getting into committing crimes and getting into prison in this exact same sort of scenario numerous times over and over and over again. I know this is getting a little far-fetched, but that, work with me. What should you do then? You're saying stay silent. Why? Because we just said that's like the worst thing you can do in both cases. Yeah, okay. So if you're going to do it 5 times, right? And let's say if you do it 5 times, but player B is, let's just say that they sort of, I shouldn't do 5 because I can't divide that. That's an odd number. Let's do it 6 times. So if we do it 6 times, I like the idea. Let's do 10 times because the math's easier. If we do this 10 separate times and you go through this process 10 separate times, if they're doing it randomly and you always defect as a result of that, you're going to get on average 2.5 years each time, right? Because it's just sort of a random thing. So over 10 times you'd lose 25 years. Whereas if you both are you're going to be doing this over and over and over again with each other. If you always stay silent, yes, you're going to get 1 year every time, but over 10 times you're only going to get 10 total years. So this becomes a better outcome as long as you guys can reliably stay and cooperate with one another. And if you know you're going to keep encountering each other more than one, in that same scenario over and over again, this becomes a beneficial scenario to go in. Where you're both cooperating with each other. You're both staying silent. Do you buy that? Does that make sense? So if you can kind of rely on each other, because if you defect now, you're going to get punished the next time. So if you can keep playing nice with your partner every time, yes, you'll do a little time now and then, but you're only going to do about 10 years over 10 different trials instead of 25 years over 10 trials if they're just kind of going at random between those two options. So the key point is that reciprocity, so this is kind of an example of reciprocity though. This is to try to bring this back to this example of social behavior. Reciprocity is likely to evolve when individuals are going to be encountering each other over and over and over again. If you will never see the other individual ever again, there is no point to be nice to them. But if you're going to see them over and over and over again, you're going to develop a relationship with them where if you're nice to them, they'll be nice to you, and you both benefit from that kind of cooperation, that interaction. Then reciprocity can evolve and will be favored by natural selection. This is the argument. Does that make sense? So the cool thing about this is that this gives us an alternative mechanism that we can use to explain why someone would do something that appears to be costly for the benefit of another individual without having to invoke kin selection. We don't have to have relatives involved for reciprocity to work. It's just relying on the fact that you're going to see them more than once and you're developing a sort of social relationship with that individual. Okay. So, this is a table from the prior version of your book. Your current book kind of removed it, but I really like it just because I think it does a good job of trying to summarize and put all these different ideas together. It's kind of going, in a way, it's harkening back to that figure. that I showed you, the sort of 2x2 grid with the pluses and minuses and stuff in it. Just to kind of run through them. So different kinds of social interactions. There are many different, basically, kinds of mutual benefits that you get. So mutually beneficial behavior can involve like straight up cooperation, where both individuals gain direct fitness immediately. You can also have postponed cooperation, where an individual, by helping, will get direct fitness from that, but they do it later. This is like the inheritance, or the some other sort of example where you're paying a cost now, but you'll get some benefit for that later on. Reciprocity is kind of the same thing, except you're going to benefit later from that same individual that you were helping, and that's sort of an additional criterion for that one. So these are, all three of these are sort of these situations where you have these mutually beneficial relationships. Sometimes the mutualism is immediate, sometimes it's more delayed. Like true altruism would be what's considered here to be maladaptive altruism, where you are losing inclusive fitness and another is gaining some direct fitness from your actions. And we don't tend to see that kind of thing very often in nature. In fact, if we think we're seeing it, we should probably be looking for other explanations, because it's very unlikely to ever be favored by selection, because you're just straight up losing fitness. Adaptive altruism would be that kind of altruism we saw in the prior chapter, where you may be paying a direct cost, but you're benefiting through indirect fitness. So you're benefiting by raising additional non-offspring, but they're relatives of yours. So you're getting more nieces and nephews, for example, or more sisters. And these last ones are kind of these other sort of weird cases of spite, which is where you're losing inclusive fitness, basically to cause a loss of inclusive fitness on another. Selection won't favor that because you're losing from that sort of behavior. And then this is sort of a weird one where player B is cheating and exploiting you or manipulating you somehow such that you are kind of being maladaptively altruistic towards them. We're not going to talk about those kinds of cases either. But again, I think it's a nice framework for understanding these different kinds of social interactions. So what I want to do, I don't have time to do the case study now, so we're going to have to do that on Tuesday. That'll actually probably be most of what we do on Tuesday, but that's okay. I think it's a good one. We are going to be talking about these Belding's ground squirrels, and I'm going to play you a quick video. Maybe I won't. I'm just going to stop. I was just thinking I'd fill some time, but the thing that's interesting about these guys is they do alarm calls, and they're kind of this annoying little chirping noise. But they do these, and by performing alarm calls, they're doing so when they see a predator, and they do make themselves more visible to predators. So the puzzle for our case study will be to try to understand why is it that individuals are performing alarm calls, because it seems like a thing where they're paying a cost, they're making it more likely they're going to get killed by a predator for the benefit of other individuals in their group. So that's going to be our goal for Tuesday. So I will see you guys then. Well, I'll see you then, but I will also see you this afternoon for our lab. We're going to play on Match.com.